Polymer characterization is the analytical branch of polymer science. The discipline is concerned with the characterization of polymeric materials on a variety of levels. The characterization typically has as a goal to improve the performance of the material. As such, many characterization techniques should ideally be linked to the desirable properties of the material such as strength, impermeability, thermal stability, and optical properties. Characterization techniques are typically used to determine molecular mass, molecular structure, morphology, thermal properties, and mechanical properties. The molecular mass of a polymer differs from typical molecules, in that polymerization reactions produce a distribution of molecular weights and shapes. The distribution of molecular masses can be summarized by the number average molecular weight, weight average molecular weight, and polydispersity. Some of the most common methods for determining these parameters are colligative property measurements, static light scattering techniques, viscometry, and size exclusion chromatography. Gel permeation chromatography, a type of size exclusion chromatography, is an especially useful technique used to directly determine the molecular weight distribution parameters based on the polymer's hydrodynamic volume. Gel permeation chromatography is often used in combination with multi-angle light scattering (MALS), low-angle laser light scattering (LALS), and/or viscometry for an absolute determination, that is, independent of the chromatographic separation details of the molecular weight distribution as well as the branching ratio and degree of long-chain branching of a polymer, provided a suitable solvent can be found. Molar mass determination of copolymers is a much more complicated procedure. The complications arise from the effect of solvent on the homopolymers and how this can affect the copolymer morphology. Analysis of copolymers typically requires multiple characterization methods. For instance, copolymers with short-chain branching such as linear low-density polyethylene, a copolymer of ethylene, and a higher alkene such as hexene or octane require the use of analytical temperature-rising elution fractionation (ATREF) techniques. These techniques can reveal how the short-chain branches are distributed over the various molecular weights. A more efficient analysis of copolymer molecular mass and composition is possible using GPC combined with a triple detection system comprising multi-angle light scattering, UV absorption and differential refractometry, if the copolymer is composed of two base polymers that provide different responses to UV and/or refractive index. Many of the analytical techniques used to determine the molecular structure of unknown organic compounds are also used in polymer characterization. Spectroscopic techniques such as ultraviolet visible spectroscopy, infrared spectroscopy, Raman spectroscopy, nuclear magnetic resonance spectroscopy, electron spin resonance spectroscopy, X-ray diffraction, and mass spectrometry are used to identify common functional groups. Polymer morphology is a microscale property that is largely dictated by the amorphous or crystalline portions of the polymer chains and their influence on each other. Microscopy techniques are especially useful in determining these microscale properties, as the domains created by the polymer morphology are large enough to be viewed using modern microscopy instruments. Some of the most common microscopy techniques used are X-ray diffraction, transmission electron microscopy, scanning transmission electron microscopy, scanning electron microscopy, and atomic force microscopy. Polymer morphology on a mesoscale, nanometers to micrometers, is particularly important for the mechanical properties of many materials. Transmission electron microscopy in combination with staining techniques, but also scanning electron microscopy, scanning probe microscopy are important tools to optimize the morphology of materials like polybutadiene polystyrene polymers and many polymer blends. X-ray diffraction is generally not as powerful for this class of materials as they are either amorphous or poorly crystallized. The small-angle scattering like small-angle X-ray scattering (SAS) can be used to measure the long periods of semicrystalline polymers. A true workhorse for polymer characterization is thermal analysis, particularly differential scanning calorimetry. Changes in the compositional and structural parameters of the material usually affect its melting transitions or glass transitions, and these in turn can be linked to many performance parameters. For semicrystalline polymers, it is an important method to measure crystallinity. Thermogravimetric analysis can also give an indication of polymer thermal stability and the effects of additives such as flame retardants. Other thermal analysis techniques are typically combinations of the basic techniques and include differential thermal analysis, thermomechanical analysis, dynamic mechanical thermal analysis, and electric thermal analysis. Dynamic mechanical spectroscopy and electric spectroscopy are essentially extensions of thermal analysis that can reveal more subtle transitions with temperature as they affect the complex modulus or the dielectric function of the material. The characterization of mechanical properties in polymers typically refers to a measure of the strength of a polymer film. The tensile strength and Young's modulus of elasticity are of particular interest for describing the stress-strain properties of polymer films. Dynamic mechanical analysis is the most common technique used to characterize this viscoelastic behavior. Other techniques include viscometry, rheometry, and pendulum hardness.